All right, so we're going to go over how to calculate area, which is the same thing as probability, under the standard normal curve. So our example, I have this like kind of graph here prepared. So on the left here, we have a graph, and I am going to assume that you already know the normal shape. So we can see by shape, it's normal. So if you're not familiar with the bell curve or the introduction to the normal distribution, go review that before you come back to finding area or probability. But just getting acclimated with that normal curve, the first question I have is, what is the mean height of American females? So the main idea here is the middle of this graph is equal to the mean. So the mean of American females is 65 inches if we're talking about their height. Again, most importantly, we recognize that the center is the average, and then each tick mark is the standard deviation. So if this was the center, and then you can see that these tick marks are the same distance away from each other, each of those tick marks is a standard deviation away. So here I added 3 to 65, here I would have subtracted 3 from 65, so the standard deviation is 3 inches. So what is the probability that a randomly selected American female is shorter than 62 inches? So in other words, as a symbol, what we're looking for is we're looking for the probability that some female who has a height that is an X value is going to be less than 62 inches. So what we do on our normal curve is we say, okay, well, here's our border, and any height that is less than 62, so like 61 or 59 or any of these heights here, would be okay. They would satisfy our condition of being less than 62 inches. What we notice, this is directly on a standard deviation, right? It's on one of our standard deviations away from the average. So if that's true, we happen to have this fancy little rule here. If we know exactly how many standard deviations away something is, we can use our reference. So we look at this table, it is one standard deviation to the left, and we've shaded in every piece after that. So on our reference here, one standard deviation to the left, and we've shaded in everything after that. So we'd have 13.5% plus 2.35% plus 0.15%. So all of these individual pieces here add up to 15.75%. So that's our answer, 15.75%. Or as a decimal, it'd be 0.1575. So that's just one normal curve to get acclimated. We're going to look at another normal curve. This one is now showing the weight of American males, and that is represented in pounds. So we can see that the mean is in the middle. So the mean of American males is about 200 pounds. The standard deviation, we can see they've ticked off those standard deviations for us on the x-axis. So each one of those tick marks is a distance of 15 away from each other. So the standard deviation is 15 pounds. So they ask us, what is the probability that a randomly chosen American male weighs between 185 and 215 pounds? And again, notice how these are nice and checked off for us. So here's 185 pounds, here's 215 pounds, and I want to figure out the probability, or in other words, the area of the curve that's in between them. So again, what we notice is it's really nice because both of those borders fall directly on exact standard deviations. So if I do it here, I'd have 34% and 34%, which is 68%. And again, what is that representing? We are looking for the probability that some random male was less than 215 pounds, but bigger than 185 pounds. So some basic questions of finding area and probability are fairly easy if the cutoffs that we're using fall exactly on whole number standard deviations away. Like I said here, they fell exactly on our tick marks. They're each one standard deviation away, or this was exactly one standard deviation away. So what happens though if that question isn't on a perfect standard deviation? So for instance, what if I wanted to find the probability that a randomly selected American female is shorter than 66.5 inches? Well, again, I could visually represent it. This height right here is about 66.5. And I would want all the heights that are below that, so I'd shade in all of this stuff here. But again, a problem with that is if I go to my reference doesn't tell me any percentages that are in between standard deviations, right? It doesn't tell me how much that would be if I move the border. Just like with this question, what is the probability that a randomly selected male weighs less than 207.5 pounds? Well, again, I could estimate 207 to be right about there, maybe, just as a rough estimate. So I'll label that as 207. And then if I want the weight to be less than that, I'd be finding all of this stuff here. But again, what I notice, I'm just going to move that line over a teeny bit. I just want to make it a little more accurate. But what I noticed, though, is, again, with that, I can't find it. I can't go to this reference because my border isn't exactly on a whole number of standard deviations. But what I'd also ask you to see is that these two pictures look almost exactly the same. The only thing that is different is the numbers that I've used on the x-axis. But what I would ask you to see is, like, this area here that I've highlighted in pink or magenta looks almost exactly as the same area here that I've highlighted in blue. So in other words, if I come down here and I draw a picture like this, and then shade in the rest of it, this area also looks exactly like the area up top. The only thing that has been changed is the label on the x-axis. So whether I'm talking about heights of American females or weights of American males, or whether I'm just don't tell you what those numbers are, what we can see is the area is independent of the labels. So for instance, if I was able to go find out that this was, like, I'm just gonna make it up, maybe this was 78%. Well, this is the same exact picture, so that would also have to be 78%. So what we're getting at is, if I have a border that's not exactly on standard deviation, what we can do is we can use a different model called the standard normal curve that doesn't use specific labels like pounds or specific labels like inches. It just uses numbers like 0, 1, 2, and 3. So this standard normal curve doesn't have a reference like individual pieces, but somebody figured out no matter where you put your little line, I've made a reference of what all the areas are behind that line. So this should have been given to you in class, or you have the ability to find it. But what we're seeing here is, like, these two pictures look really similar. So if I could find out what the area is from this reference, it's going to be the same thing over there. So that's our main idea of using the standard normal curve. So let's go do an example problem for that. And what we notice here is that we are going to have temperatures of a city being normally distributed. So what that means to us is we can draw a normal curve. We know it's centered at the average, and it tells us the mean temperature was 55.2, and then each standard deviation is 6.3. So one standard deviation away, I would take 55.2 and subtract 6.3. So I get about 48.9. I'll do that again. If I subtract another 6.3, the next standard deviation away would be 42.6. If I go the other way, starting at the average and adding one standard deviation, I get 61.5. And if I do that again, the next standard deviation would be at the label of 67.8. So I'm getting a basic picture of what our temperature distribution would look like, very similar to these types of questions up here where we were just labeling the average and then the standard deviation. But on this one, what they're looking for is we're looking for the probability, so P for probability, that a randomly chosen day, which we're just going to call an X value, is colder than 45, so it's less than 45 degrees. Now what we notice, if I were to go estimate where 45 degree was, it's maybe somewhere in here, and being colder than that would be this way. Now that doesn't fall directly on a nice standard deviation, so what that means for us is we have to go use this thing called the standard normal curve, which uses a common unit called z. So there's a little formula to convert x to z. So to get z, we take our x value, we subtract the average, and divide by the standard deviation. So in this situation, the x value that we're concerned about is 45. We subtract the average of the distribution, which is 55.2, and we would divide by the standard deviation. So obviously I encourage you to do that on your own calculator to make sure that you're getting the right answer. And when we do this, we're always going to round to the second decimal place. So I get negative 1.62. So what I'm saying then is instead of asking when the probability is less than 45 degrees, which I can't do because it doesn't fall on a perfect standard deviation mark, I've changed the question to asking what is the area behind the z-score of negative 1.62. Now again, similar to questions that we did know, we just went to a reference if they fell on perfect standard deviations. If they don't fall on perfect standard deviations, we have to go to a different reference. So this line that we've put in here is still the z-score of negative 1.62. We just did a unit conversion. I could call that 45 degrees, or I could say that's the same thing as z equals negative 1.62. So how do I find the area that's behind that border? Well, we have to pull out our table, and this again would have been provided to you. So our z-score is negative 1.62. So what we'll see here is this table shows us the area behind whatever z-score we look up. So this side is showing positive z-scores, so I have to go find the reference that has a negative z-score. So again, if I tell the table what this border is, it'll tell me the area behind it. So in our situation, our z-score is negative 1.62. So on the left side here, I find negative 1.6. So it's going to be one of these numbers here. And then the last digit is a 2. So on top, I find the last digit of a 2, and I see where they intersect. So they intersected at this number here. So the area, or the probability, we want to think of it as the same thing, is 0.0526. Or you could write that as 5.26%. Let's go ahead and do another one a little bit quicker this time. So on this one, if I redrew that standard normal curve, I know it's centered at 55.2. What we're looking for now is we're looking for the probability that a day is cooler than 37.5 degrees. Well, 37.5 degrees is like way over here. So I'm seeing the area behind that's pretty small, but it doesn't fall on a perfect standard deviation necessarily. So let's convert that to z. So we take our x value, and we would subtract the average. We would divide by standard deviation. So when we do that on our calculator, we get the z-score of negative 2.81. And again, I'm rounding to that decimal. So how do I find the area that's in that teeny little tail? Again, if this was the z-score of negative 2.81, well, what I would do is I'd go to my reference again. So I find the z-score that starts with negative 2.8. So here's negative 2.8 on my z. So here's negative 2.8. And then the last digit is supposed to be a 1. So where does the 2.8 row intersect with the last thing that's a 0.1? Well, the place where they intersect is right here. So the area, or the answer to our question, what is the area in that tail? 0.0025, or is, if you want it as a decimal, and as a percent, it would be 0.25%. Either one of those is accurate. So moving on to the next one. This one, again, we're working with the same normal distribution. So I'm just going to sketch it. But now in this case, they want us to find the probability that a randomly chosen day is colder than 45 degrees, but also warmer than 37.5. So if I tried to estimate that from kind of our examples from before, this might be about 45 degrees, and maybe this is about 37.5 degrees. But again, neither of those, and I want the area in between, neither of those is on a perfect standard deviation. So I'd have to convert those to z-scores. And we actually already did those z-scores in the first two examples. So the z-score of 37.5 was the same thing as negative 2.81. And instead of x's, we've converted that to z's. And instead of 45 degrees, that x value would be z-score from above would be negative 1.62. So how do we do this? Well, if we went to our table, we know that this z-score, the 45 degree z-score, which was negative 1.62, if we started there and shaded all the way to the left, that gave us 0.0526. In the example before that, or the one we just did, we've calculated the area to the left of this z-score, which was negative 2.81. We said going this way, that would be 0.0025. So if I use some shading here, we can see that all of the orange is too much area. So I'd want to take away the blue to be left with this little part here. So we would take the probability of our first one, so the big one, which was 0.0526. That's all the way less than 45. And we'd take away the area, 0.0025. That's just the area that's less than 37.5. So the area in between those two would be 0.0526. 0.501, or if you want it as a percent, 5.01%. And again, here, if we have an in-between, we took the bigger area and subtracted the smaller. Last example for today is going to be the probability that a given day is warmer than 60 degrees. So our average is 55.2. And again, if we come back and look at our original one that measures all the standard deviations, 60 degrees is not a perfect standard deviation. I could estimate where it is. It's about, I don't know, maybe like right there. And if it's warmer, I want to go this way. Now, as symbols, how we're going to write that is we are looking for the probability that any day, the temperature is just some random thing, so we'll call it X. What are the probability that that's going to be bigger than 60? Well, again, this is not a perfect standard deviation away, so we can't use X's. We need to convert that to Z's. So the first thing we'll do is we'll get the Z-score. So the Z-score would be the X value, so 60, minus the average of 55.2, divided by 6.3. So on our calculator, we get the number 0.76. So in other words, instead of calling this border 60 degrees, we could also call this border Z equals 0.76. So once I get Z, I can go over to my table. Now with the second example, or the last part of this, is we notice that our table only ever shows us area to the left of a Z-score. So on this one, when I'm looking for the area to the right of a Z-score, I have to do one extra little step. So first, I am going to look up the Z-score, so 0.76. So in other words, it starts with 0.7. So it's somewhere in this row. And then it's supposed to end, the last decimal is a 6. So if it ends in a 6, that's where this row ends in a 6. So where those two intersect is this number, 0.7764. But recall that this table is only showing us the area to the left of that cutoff. So this 0.7764 is actually this side. So if I want the other side, this side, well, we know the total area, if I highlighted everything, would be 1. And then I want to take away the area to the left of my border, which would just leave me with the area to the right of the border. And that comes out to be 0.2236, or if you wanted, 22.36%.